Hi everyone, and welcome to section 9.2. Today we're going to look at vector formulation. Now, if we define the vector x1 to be the functions e to the 5t cosine 2t and x2 to be t squared and plus 1 and 10, let's compute 3x1 plus 5 x2. Okay, well, how would you do that? Well, you would treat it much like you would a vector with scalars instead of functions as inputs. So if we go 3x1, okay, that's 3 times e to the 5t cosine 2t plus 5x2, that's t squared plus 1 and 10. What do you end up outputting? Well, 3e to the 5t plus 5t squared plus 5 and 3 cosine 2t plus 50. So vector addition is going to work just like it would for scalars and as opposed to functions. Now the only thing that would be somewhat new is what does x1 prime look like? Okay, in which case you're going to take e to the 5t, okay, and take the derivative of that, get 5e to the 5t, and you'll take the derivative of this and get minus 2 sine 2t. So you take the derivatives component-wise. Okay. How to convert a system of differential equations to a vector differential equation. Okay, so in short, let's think of x of t to be a vector with n functions of t. Then the derivative, we define the derivative x prime of t to be the derivative of each component-wise. So if you look at the system of differential equations like this, on the left-hand side, really what we are describing is x prime of t. Okay, so its components are x1 prime and x2 prime, so let's refer to it as the vector x prime. Okay. On this side, we can rewrite this as the 2 by 2 matrix 4, 2, negative 1, 1 times x1, x2. The matrix, the 2 by 2 matrix we call A is called the coefficient matrix. Okay, and this is an example of a vector differential equation. Now, our whole goal in this is to find functions x1 and x2 that solve this differential equation. Okay, and to find those functions, we're gonna, it's not gonna be to find those functions. As part of this, we're gonna need to know how to test if functions are linearly independent. Okay, so what does that mean? Okay, and this is the last little bit from this section. This will be a really short video. It's kind of a build-up to a greater result. Functions f and g are linearly dependent if there exist constants a and b not both 0, such that a times f of t plus b times g of t is equal to 0 for every t. Okay, so you have two non-zero constants that, when multiplied by f and g, sum to 0 for any value of t. They're independent if a of t plus b times g of t implies that a equals 0 and b equals 0 for all t. Now, one way to test that is through the Wronskian. Okay, so in a 2 by 2 case, okay, we compute the determinant of, across the top row is the functions f and g. On the second row are the functions f prime and g prime. And if this was a 3 by 3 case, you'd go f, g, h, and you'd go f, f prime, f double prime, g, g prime, g double prime, h, h prime, h double prime, and so on. Okay? And to, just like with determinants, if you get the determinant, let's kind of take a look. we'll see what the result is instead of me stating it. So let's look at the functions 2t squared and t to the fourth. Now clearly, there's not a constant that you can multiply a by a pair of non-zero constants that you can multiply f and g by. G of t, that outputs 0. Okay, a times 2t squared plus b times t to the fourth is 0 for every value of t, only when a and b are both 0. So we know that these are two linearly independent functions. Let's see what the Wronskian, how the Wronskian outputs. So we have 2t squared, and we have t to the fourth. The derivative of 2t squared is 8t squared, is 4t, and this is 4t cubed. Okay, so let's compute the determinant of this and see what we get. You get 2t squared times 4t cubed, that's 2 times 4 is 8, t to the fifth minus 4t and t to the fourth, that's 4t to the fifth, which is 4t to the fifth, which is not 0. And that's the most important case. So linearly independent functions will have a Wronskian that is non-zero. Can you spot the one that has the pair of functions that are linearly independent? Okay. Not sure about the middle one. Okay, that's maybe not as obvious, but the bottom one certainly is. E to the t and e to the t plus 3. Okay, because the function g of t is e cubed times larger than the function f. So let's look at what the, make sure that the Wronskian outputs 0 for that. So we have e to the t, and the derivative of e to the t is e to the t, okay? We have e to the t plus 3, and the derivative of e to the t plus 3 is e to the t plus 3 times the derivative of t plus 3, which is 1, okay, using the chain rule. So now we take the determinant of this, we get e to the t times e to the t plus 3 minus e to the t times e to the t plus 3, and that equals 0 for every value of t. Okay, so that's a clear linearly dependent pair of functions. So now what about the middle one? You have 9 cosine 2t and 2 cosine squared t minus 2 sine squared t. Okay, so we got 9 cosine 2t. What's the derivative of that? It is what? Negative 2 times 9, that's 18, sine 2t. And 2 cosine squared t minus 2 sine squared t. And the derivative of this, 2 times 2 is 4 cosine t times the derivative of the inside, which is a negative sine t, minus 4 sine t times the derivative of sine, which is cosine t. Okay, I should clean that up real quick. Minus 4 cosine t sine t minus 4 sine t cosine t. That looks like it's minus 8 sine t cosine t. That way we don't have like terms unsimplified. Now, let's take the determinant. 9 times 8 is 72, so negative 72. cosine 2t times the sine of t cosine t minus negative 18, so that's plus 36 sine 2t, negative 18, so this will be minus 36 sine t sine, oops, I messed this up. Sorry about that. Let me start this over again. So we get negative 72 cosine 2t minus cosine 2t times the sine of t cosine t minus, go negative 18 sine 2t times 2 cosine squared t minus 2 sine squared t. There. That's better. Now, one thing you'll notice that we have going around is cosine and sine functions that have an argument of t, and cosine and sine functions that have an argument of 2t. If at all possible, we should try to combine them so that their arguments are the same, because otherwise it's going to be very difficult to simplify it and make any sense of what we're working with here. So there's a half angle identity that says that the sine of 2t is 2 sine t cosine t. Okay, so if I were to use that, the sine of t cosine t is equal to the sine of 2t over 2. So I'm multiplying that by cosine 2t, multiplying that by negative 72, and what I end up getting is negative 36 sine 2t cosine 2t. Okay, so that's here on the left-hand side. What do we get that's on the right-hand side? There's another trig identity that says the cosine of 2t is cosine squared t minus sine squared t. See, that's in the screen. Yeah, you can see that. So if you look at this, this is 2 times that. So I can replace everything here with 2 cosine 2t. So as we take care of these negatives, we have minus a negative, so that's now plus. And this is 36 sine 2t cosine 2t. So negative 36 sine 2t cosine 2t plus the 36, the same thing, that equals 0, and therefore f and g in the middle are linearly dependent functions. All right, so that was probably the most complicated one I could give you. And again, this section, the very important part is converting a system of differential equations to a vector differential equation. This right here is something a little bit, I would say, is more intuitive to students, knowing when functions are linearly independent and when they aren't. I think we've actually even said it earlier in lecture, 2 linearly independent functions, and we kind of knew what we were talking about. Basically, there are functions that satisfy these two definitions, but they're the same definitions that we use for vectors, okay? Where functions f and g are linearly dependent if their constants a and b not both zero, such that a linear combination is zero, but they're linearly independent if the only way for this to output zero is for a and b both to be zero. All right. Hope this video finds you well, and take care. We'll see you in section 9.3.